But I guess there are groups that try to get more parameters like effective temperature, mass, and age. And so this is, I think, the next important update of these catalogs to feed them with more parameters.
Thank the speaker one more time.
Okay, that's fine. And then okay. Great. Good morning, everybody. I'm so excited to share with you the results from our long-term project of a long-term spectroscopic survey of the very nearest mid to late fully convective M dwarfs. And I'd like to just thank my collaborators who are listed up here. So we have motivation for this project is that, of course, we all know that we can only understand our planetary discoveries as well as we understand their host stars. And there's a lot that we don't know still, there's a lot of things that we would like to still know about these mid to late M dwarfs. And so this project was an attempt to spectroscopically characterize the sample so that we can understand their ages and activity levels and multiplicity rates. So in addition, there is this observed trend of stellar multiplicity fraction as a function of primary star mass, and it's a decreasing trend with primary star mass. And by that, I just mean that, you know, the most massive stars are almost 100% of the time have lower mass stellar companions. But then when we get down to the M dwarfs, that multiplicity frequency drops to about 26%, right? But why is this? Why is this? So we want to know, is this kind of multiplicity rate imprinted at birth, or are most stars born 100% multiple, and then maybe the lower mass stars tend to lose their companions over time, or is there some other explanation? So we created a sample of mid to late M dwarfs within 15 parsecs, and I'm going to use the phrase mid to late M dwarf, but what I really mean is M dwarfs with masses between 10% to 30% the mass of the sun, because mid to late M dwarf rolls off the tongue much more easily. So we created this all sky volume complete mid to late M dwarf sample, and I show here I'm going to show their positions projected onto the sky. And so when we began our project, only about a third of this sample had high resolution spectroscopic observations of any kind in the literature, right? And I just made a cut at about 20,000 resolution as high resolution. Roughly about another third had low resolution observations. But roughly a third of this sample, the very nearest fully convective stars within 15 parsecs, had no existing or published spectroscopic information. And as you can see, most of these stars are in the southern hemisphere. So because this is an all-sky sample, we used high-resolution spectrographs, the TRACE and Chiron spectrographs on 1.5 meter telescopes in the northern and southern hemisphere for our observations. And our goals were to get at least 4 observations of every single star over what has turned out to be about 6 years. And so we wanted to measure rotational velocities, radial velocities, and the multi-epoch part of the radial velocities is to detect any objects that had velocity variations. But we could also detect, you know, double and triple line systems within the sample. We wanted to measure orbits for those that were short enough for us to get full coverage. And then from all of those radial velocities, including the systemic velocities from the spectroscopic orbits, we could calculate 3-dimensional galactic space motions. So in addition, Emily Pass led the effort to measure H-alpha equivalent widths for the single stars in this sample, and she published those results last year. And then further, this is obviously not spectroscopic, but we got test data on almost all of these stars. And Amr Medina led the effort to measure the flare frequency distributions of these single stars in the sample. And also both she and Emily measured new photometric rotation periods for many of the stars in the sample using TESS and MIRF data. So we're getting there in terms of activity. So here's what our, as I said, we got at least 4 observations of every single star. So we're able to kind of characterize our precision. So this is the standard deviation of our V sin I measurements, our rotational broadening measurements for every star. And they're color coded by the spectrograph that we used. And then I've also noted the ones that have V sin I's or rotational broadening larger than our detection limit of 3.4 kilometers per second. And you can see that we do fairly well. We do less than about a kilometer per second for most of the stars in our sample, but there's these faint broadened stars that we do worse for. And then we did the same type of thing for our radial velocities. And I want to highlight Emily on this slide because she is responsible for the data on this plot. Like she spent a lot of time characterizing the uncertainties on our radial velocities. And so because of her, we're able to get, for the slowly rotating objects, we have uncertainties at about less than about 30 or 40 meters per second per, for our intrastar radial velocity precision. And then even better than a kilometer per second for even the highly broadened or the rapidly rotating stars. So with all of these radial velocities and in hand, we're able to plot a Toomre diagram and calculate our UVW space motions, our 3-dimensional space motions, using the parallaxes that we have. And I'd like to point out that most of our parallaxes are Gaia, but they are supplemented for especially the multiple systems with ground-based parallaxes. So we're able to use our parallaxes and proper motions and the radial velocities that we've just measured to calculate our UVW space motions. This is a Toomre plot, which shows the velocity component in the rotation of the disk, plotted as a function of the tangential velocity component. So in and out of towards and away from the galactic center, and the W component is up towards the galactic North Pole or South Pole. And so and I want to just highlight that these dashed lines are not intended to demarcate any population. Those are just constant velocity lines. And so we calculated the probability of thin and thick disk membership for all of our stars. And so those are noted here in blue, and we find that roughly 80% of our stars are highly probable thin disks, so they're younger. So the thin and thick disk population membership are proxies for relative age, right? So the thin disk members are younger than the thick disk members. We calculated that the probability is that these red stars are the highly probable thick disk members. And then the remaining kind of teal squares are ambiguous population membership. So that's not too surprising. Most of our sample are thin disk members. Some are thick disk members. But we can, we can also explore the rotational broadening measurements of our sample as a function of the masses of our stars. And I've note that I've got mass plotted, the most massive stars plotted to the left. And I've got our 3.4 kilometer per second detection limit noted there. And it turns out, of course, that most of the highly broadened or rapidly rotating stars are thin disk members, but they only make up about 30% of our sample. Most of our sample are slowly rotating, minimally broadened stars. And we also have photometric rotation periods for almost all of these. And they have rotation periods less than about 5 days, just for you to know. So we also have detected, in addition to previous work where we've published spectroscopic orbits, we've detected some new binaries. So this is a long-term, there's a velocity trend of GJ512b and indicates a long-term companion. We've measured some new spectroscopic orbits for these double line binaries. And it also turns out if anybody was worried about this system, GJ865 is a triple lined binary. So we're getting more data, or triple line triple, sorry. We're getting more data to fit the orbit for that system. So with all of these systemic velocities now in hand for our multiple systems, and the majority of the multiples kind of noted in the sample, we can calculate an overall stellar multiplicity rate of 21% for the entire sample. And you know, we've doubled the number of known brown dwarfs in this sample from 3 to 6 with our spectroscopic work. And so we can calculate a brown dwarf multiplicity rate of 1.6%, which is very, very much in line with the 1.5% rate for solar type stars. And so I've noted the binaries or the multiples all here in these pale green dots. And so one of my motivations was to understand if there's an age relation with multiplicity, right? Do M dwarfs lose their companions over time? And so we can do that with these, you know, these thin and thick disk populations. We can calculate whether there's any difference in the multiplicity rates, but using only the highly probable thin and thick disk populations. And it turns out that there's no difference. So within our uncertainties, there's no difference in the multiplicity rate. So this seems to hint that stars seem to be born with their multiplicity rates imprinted. Obviously, we need a larger sample and more data. You know, that's always the answer to actually confirm this. But this is somewhat surprising because some people have thought that all stars are born multiple and that things just happen and stellar evolution happens and things get stripped. So I'd like to just note that our sample, now that we have all these nice spectroscopic data for our sample, this informs a target list for future missions. And a lot of these stars are going to be part of the ESCAPE mission target list, which is an EUV stellar characterization mission led by Kevin France and with project scientist Allison Youngblood, who's here if you want to ask her about any of that. So just in conclusion, we've done this amazing thing. We've measured multi-epoch, high-resolution radial velocities and V-sign I's for a volume-complete all-sky sample of mid to late M dwarfs within 15 parsecs. Most of them are slowly rotating or minimally broadened. We find a multiplicity rate of 21% for this sample at all separations and all orbital periods. And we find no significant difference between the multiplicity rates of the thin and thick disk populations. And then just with these data, we've tripled the number of these fully convective stars that have high resolution spectra and exquisite astrometry and photometry. So thank you so much. I'm happy to take questions.
Well, the next speaker.
All right.
These exquisite spectra, what are the prospects for measuring chemical balances with your spectra?
I think, so they're exquisite spectra, but they are not very high signal to noise. So I'm not sure about those prospects. I'm not sure that they're high enough signal to noise for that. What's that? Exactly. Sorry, I'll repeat the question from now on. Sorry.
Yeah, hello. So you mentioned with the photometry, the variations. I was wondering, for the samples, any of the photometry capable of like a transit photometry, or is it not really anything in the sample of that case?
You mean eclipsing binaries?
Essentially, yeah.
Yeah, so in the kind of overflow sample, we've detected one eclipsing binary that's eccentric. And so we only see one eclipse, but that's in the test data. And then, of course, there's planets. There's 7 transiting planets in this sample, and about 25 total systems have all types of planets. Known planets.
Great work, Jen. I love your kinematics work, especially.
Oh, thank you.
How did you assess the completeness of your sample?
So we yeah, yeah, exactly. So oh, thank you. So I did my PhD work with the Recons group, and we have been measuring parallaxes in the Southern Hemisphere for many years. So we used Gaia initially. I did a cull of the Gaia catalog and then filled in the remaining ones that Gaia didn't have with the parallaxes that the stars already knew that were within 15 parsecs. It's a Pat's job. Yeah.
Thank the speaker one more time.
One and then 15 minutes total.